Hi, I'm Amir Hossein Mirzabozorg, and in this video I want to talk about tensile test and welding simulation of a lap joint in a multi-step analysis via Abaqus. How to ask your video-related questions. Don't hesitate to ask any questions you might have about the explanations presented in this video using the comments below. We try to answer all questions regarding the video details in the comments below. I did the welding simulation according to this paper. Computer analysis of thermal phenomena and deformation in lap joint welded by a laser beam. In this article, the thermomechanical analysis is conducted via semi-coupled analysis. First, the thermal analysis is conducted using the heat transfer step, and then the calculated temperature field is imported to the mechanical analysis, and the mechanical analysis is conducted using the static general step. But in my simulation, I used the coupled temp displacement step to do the fully coupled thermomechanical analysis. Here, some explanations are written about the interaction between the plates and defining the thermal interaction. This is the volumetric heat flux equation that must be implemented via the DFLUX subroutine. And this is the geometry of the modeled, and this is the moving heat flux. And this is the mesh of the model. I use this mesh for my model. And the material has been defined according to these curves. The laser beam power is equal to 1500 watts, and the speed of the heat flux is this value, and the laser beam radius is equal to 1 millimeter, and the laser penetration depth is assumed to be 4 millimeter. And this is the temperature contour, and this is the simulated moving heat flux. And this is the temperature field in the thickness direction. And these mechanical boundary conditions are defined during the welding process. But in my simulation, I defined another kinds of boundary conditions. And I define boundary conditions only at the ends of the plates. And this is the stress field due to the welding process. In the article, it is explained that here, perfect contact is defined for the melted zone, but the explanations are not clear enough. And to define thermal conductance in Abaqus, we must enter several coefficients and constants, but none of them are written in this paper. So, to define the interaction and to define the heat flux transmission between the plates, I define tie constraint here. And I only define mechanical contact between these regions because I didn't have the thermal conductance constants. Now I want to show you the model. This is the plate. This is the defined material. To do the fully coupled thermomechanical analysis, I define conductivity, density, elastic behavior, expansion. To account for the melting phenomena, I define latent heat and I define the plastic behavior and I define the specific heat. And to calculate the melted zone, I use the USDFLD subroutine. And to write this code, I used one state variable. So I added depvar to the definition of the material. This is the assembly. I define these partitions for meshing and for defining the tie constraint. Now I want to show you the defined steps. Step 1 is defined for the welding stage, step 2 is defined for the cooling stage, and step 3 is defined for the tensile test stage. During the welding process, the temperature is a function of position and time. So I set it to transient response. And this time period is the real time period of the welding process. And these are the incrementation settings. Step 2 is defined for the cooling stage. I define this stage according to my knowledge, and there are no explanations for this stage in the article. Also, here the response must be set to transient, and also this is the real time period of the cooling stage. Real means what has been done in the laboratory or in the test rig. And these are the settings of the incrementation tab. Step 3 is defined for doing the tensile test. And this time period is not real. It can be real or not. As the defined material is not dependent on the strain rate, here we can enter any arbitrary value. And I define 1. And these are the settings of the incrementation tab. I go to the interaction module. In the interaction module, I define tie constraint here. And I define mechanical contact. And as you can see, the interaction property is frictional and no thermal conductance is defined because I didn't have its coefficients and its constants. And I define general contact to account for the mechanical interaction. And I define convection between the plates and the ambient, and the convection coefficient is set to 10 and the ambient temperature is set to 20. Also, I have defined the radiation between the plates and the ambient, and the ambient temperature is set to 20. We have these two thermal interactions in step 1 and step 2 because they are thermomechanical steps. But as step 3 is mechanical, they are not available in step 3. Here I have defined fixed boundary conditions at both ends. And in step 3, it is modified and the displacement control loading is applied and the total value of the displacement is 3 millimeters. And the initial temperature is set to 20. And this is the thermal load that must be implemented via the DFLUX subroutine, and it is body heat flux because we have the volumetric heat flux equation. And this is the mesh of the model. Now I want to show you the subroutine. This is the DFLUX subroutine, and we have the laser heat flux only in step 1, and in other steps it's equal to 0. Now I want to show you the results. Let's see the Mises stress contour. And as you can see here, we have the necking. And let's see the temperature field. This is the laser beam spot. This is the start of the cooling step. And here, as you can see, during the cooling step, the maximum temperature decreases because of the convection and radiation. And this is the final temperature field before conducting the tensile test. Now I want to show you the melting zone. Field variable 1 illustrates the melted zone. For better illustration, I set the contour type to coils. Now I want to plot the force displacement curve. This part of the force displacement curve relates to the step 1 and step 2 because the displacement is equal to 0. Then in step 3, the displacement control loading is applied and the displacement is more than 0. You can contact me via Telegram or WhatsApp, or you can send email to me. We can have one-on-one tutoring on the AnyDesk WhatsApp and make special tutorials to your order. We can conduct high-quality simulations for your physics exercises and industrial projects. Now I want to suggest you several related videos of our YouTube channel. Thank you so much for watching this video. Have a good time. Goodbye.